Hello, my name is Garvit Goyal, and I'm going to present our work on accelerating COVID-19 diagnosis and monitoring via high-performance deep learning on CT images. The framework we developed is called Compute COVID-19 Plus. In last 2 years, coronavirus has infected around 35 million people in United States, 6 million people in United Kingdom, 1 million people in Japan, and 191 million people worldwide. Despite 50% of the population in the United States being vaccinated and 13% population being vaccinated worldwide, United States is still entering into the fourth wave of COVID-19, where the Delta variant of COVID-19 accounts for more than 90% of the confirmed cases. To compound the matters further, globally deployed RT-PCR test has mediocre accuracy and has very high turnaround time. To that end, we developed a deep learning-based framework for diagnosis of COVID-19. Our framework is called ComputeCOVID19 Plus. Our framework uses chest CT scans. Chest CT scans of COVID-19 patients show distinct features. These features are called radiological abnormalities. These include ground glass opacity, vascular consolidation, and crazy paving pattern. Our framework achieves an overall accuracy of 91% and has much lower turnaround time as compared to RT-PCR test. Our contributions are as follows. We developed novel algorithms and software for high-precision CT image construction and interpretation of COVID-19 CT scans. We evaluated the framework with respect to speed and accuracy and validated it with clinical COVID-19 data. Our framework is applicable to the diagnosis of COVID-19 and its variants, and also to other diseases which can be diagnosed using computer tomography. The framework is shown in the picture. The workflow followed by Compute COVID-19 Plus framework is shown in green arrows. First step in the workflow is enhancement of CT images acquired from CT scanner machine via enhancement AI. These enhanced images are then fed to analysis AI for high precision interpretation and diagnosis of COVID-19. Workflow we used for evaluating the efficacy of Compute COVID-19 Plus framework is shown in the slide. First step in the workflow is data preparation. For training and testing AI tools in Compute COVID-19 Plus framework, we acquired CT images from multiple data sources. Since CT images were acquired from multiple data sources, there were a lot of inconsistencies in the data that had to be addressed. For example, some of the CT images in the dataset contained a circular segmentation, which was removed during computer simulation. Second step in the workflow is image enhancement. Image enhancement is used for improving the quality of CT images acquired from CT scanner machine. Image enhancement uses a convolution neural network called DenseNet and deconvolution network, also known as TDNet. TDNet has three distinct features. First feature is the use of dense blocks in the convolution network. Compared to the existing state-of-the-art convolution network, DenseNet achieves higher accuracy and has higher computational efficiency. Second feature is the use of shortcut connections. These shortcut connections facilitate feature reuse and mitigate the problem of exploding and vanishing gradient. Third feature is the use of deconvolution network. Deconvolution network reconstructs high-quality CT images from the features extracted by convolution network. Third step in the workflow is image analysis. Image analysis is used for high-precision interpretation of enhanced CT images. Image analysis uses the workflow presented in the reference given in the slide. First step in image analysis is image segmentation. Image segmentation uses a convolution neural network called 3D anisotropic hybrid network, which segments the lung region from the input CT image. The enhanced segmented images are then fed to classification AI, which classifies them into positive and negative cases based on the features present in input CT image. Classification AI uses 3D version of DenseNet one-to-one network. Complete workflow starting from original image, image enhancement, generation of segmentation mask, image segmentation, image classification is shown in the slide. Training and testing AI tools in ComputeCOVID19 plus framework are computationally expensive processes. Therefore, we use high performance computing techniques to reduce the execution time. For training, we exploit batch level parallelism by forking multiple processes on GPUs. Each GPU contains an image of neural network which is synchronized at the end of every epoch to maintain consistency and training parameters. Inference, which is comparatively less computationally expensive than training, is implemented via OpenCL and evaluated on CPU, GPU, and FPGA. CPUs and GPUs with their high processing capability are appropriate for computer tomography applications in hospital settings, while FPGAs operating at low frequency and consuming low power are appropriate for computer tomography applications in telemedicine. To reduce the execution time of TDNet inference, we applied a set of application-specific and architecture-specific optimizations to these OpenCL kernels. The portability of OpenCL kernels allows us to evaluate DDNet inference on CPU, GPU, as well as on FPGA. However, due to the differences between the fixed architecture hardware and reconfigurable hardware, some additional optimizations were required for FPGA implementation to reduce the execution time. These include compute unit replication, intra-thread vectorization, use of dedicated kernels, and runtime deconfiguration. The table shows the performance of training enhancement AI with varying number of GPUs and batch size. The accuracy of trained network decreases with the increasing batch size. This is because the inputs from large batch size traps the optimizer in a local minima, which is closer to the initial start point. In spite of that, we were able to achieve approximately 7-fold speed up with the accuracy within the acceptable range. The inference of TDNet was evaluated on GPU, CPU, and FPGA. Best performance was achieved on NVIDIA V100 GPU with OpenCL implementation executing in approximately 0.1 seconds. The execution on FPGA is approximately an order of magnitude slower than the execution on CPU. However, considering the maximum memory bandwidth available on FPGA and its maximum operating frequency, we consider that an encouraging result. In our latest research, we were able to reduce the execution time on FPGA to 0.5 seconds by maximizing the memory coalescing in our implementation. To evaluate the accuracy of ComputeCOVID19 plus framework, we first evaluate the accuracy of image enhancement and image analysis separately, and then combine them together to analyze the overall accuracy. The result of image enhancement is shown in the figure. Enhancement AI removes almost all the noise and missing view projection artifacts present in the input CD image. Quantitatively, Enhancement AI reduces the mean square error and improves the multi-scale structural similarity index between the high-quality target image and the enhanced image. Image analysis achieves an overall accuracy of 86% and area under the receiver operating characteristic curve of 0.890. The accuracy and ROC curve of classification with original images are shown in the plots. By prepending enhancement to the analysis, we were able to achieve an overall accuracy of 91% and area under the receiver operating characteristic curve of 0.942. That is approximately 5% improvement in accuracy and 7% improvement in area under the curve. The accuracy and ROC curve of classification with enhanced images are shown in green. Improvement in accuracy with enhanced images is because of the better interpretation of features present in the enhanced image. The CD scans presented in the slide show some of the features that were not very clear in the original CD image, but became very clear and easier to interpret in the enhanced CD image. In conclusion, Compute COVID-19 Plus framework improves the accuracy of COVID-19 diagnosis via enhanced CT imaging and has faster turnaround time compared to RT-PCR tests due to better accessibility and less dependency on materials and labor. Table here compares Compute COVID-19 Plus framework with the existing state-of-the-art deep learning-based framework for diagnosis of COVID-19. We thank our sponsors and also individuals and organizations involved in data collection. Thank you for listening.